Hello. Morning, everyone. My name is Zhening. I'm very happy and honored to be the first presenter of the day, considering this is not a very exciting topic compared to those like AR, VR applications. But anyhow, I'm a first-year PhD student at University of Cambridge. Just as quick self-introductions, I belong to the Future Infrastructure and Built Environment CDT at Cambridge. I'm also the larger Digital Road of Future project some of you might be familiar with. My PhD is sponsored by National Highways and Costain, which also happen to be the sponsor of this workshop. Today, I'm going to present a piece of work we did probably half a year ago. It's titled as NHA12D, a new pavement crack data set and a comparison study of the crack detection algorithm. This is a joint work with me, Weiwei, Professor Abir, Al-Tabbaa, and Professor Ioannis, Brilakis. So this is the structure of today's presentation. I'm going to quickly cover the motivation of this work, and then some literature reviews, the methodologies we use, and we're going to dive into the implementation details and show some numerical and visual results. We will conclude this with some findings and future directions. So what's the motivation? So I'm sure most of you will know crack detection is a very old research topic. It's kind of like well established now, and every year there's tons of papers coming out trying to push the boundaries and then improve those benchmarks. However, fully automatic crack detections remains a challenge. This is because when we are developing those algorithms, what we normally do is we will come up with the algorithm and test them on the public available crack dataset. And once we prove that the algorithm we develop can outperform other algorithms by a small margin, and we claim, okay, we made the improvement. This is good, but the problem is those public available data sets are not representative enough to the real images we're going to use in practice. In practice, pavement images captured on highway has more complex background. Therefore, those algorithms that perform well on those public available data sets may not perform equally on the pavement we capture on real highways. So this is our argument. To help with this, we're thinking, since we're working with National Highways closely, National Highway is the manager of the highway in the UK. They do the pavement evaluation, inspection all the time. Why not we collaborate with them and we can present in a new data set, which is the one they really use in their practice. And then we can label them carefully and push them to public domain, and we can use this as a new benchmarking algorithms. So this is the first contribution of our work. The second one is we also present the benchmark studies. We test the different crack detection algorithms on the data set we presented. Okay, so let's look into the literature review first. So for crack detection, as I said, it can trace back to many, many years ago. And previously, we normally tackle this problem as image processing challenges. So there are two main branches. One is intensity thresholding, one is edge detections. So intensity thresholding is like we treat crack as those quite distinct pixels in images, which normally have like a darker colors or intensity. So we kind of like set the threshold and filter the images with different thresholding values, and we can generate the crack images. And we fuse them together, then we can get quite well-captured detection results. This is a quite old technique now, and we also can treat this as edge detection problems. There is quite a lot of edge detection algorithms out there, such as Kenner edge detections or super edge detections, and we apply them to the images, and we can get like a reasonable crack detection result. But these are the history now. Like since the rise of deep learning from, say, 2012, something like that, and now the most people in this domain are trying to use deep learning to do the crack detection with like end-to-end manners. So yeah, and these are the list of the models that was presented in the literatures. So that was the algorithm perspective. And look into the data set. So we have a look into all the crack detection data set, and there are like 9 to 10 of them out there. We found the common problem is that most of those data sets are captured kind of like randomly. Some of them are captured in their campus with iPhone, or some of them are just taking picture of some stone images or like wall images or rack images. And some of them also do that on pavement, but it's kind of like not doing that to systematically, or they're using what we normally use in the real project, which is the surveying vehicles. So, so this is the challenge we're trying to tackle here. Now see, how do we actually doing this? So first one, we present a data set, which is called NHA12D, National Highway A12 data set. And A12, as shown over here in the map, is one of the main strategic road network in the UK, and is managed by National Highways. So we capture some data set over there with the National Highway surveying vehicles, and some example images over there. Each images are captured a lane, one lane of the highways. And those images has quite high resolutions, which is 1920 times 1080. And we have different point of view. We have like the forwarding viewpoint, and we also have the vertical viewpoint. And because A12, they have like concrete pavements and asphalt pavements, so we cover both of them in this data set. And of course, we label them at pixel levels. We will elaborate to why it's important to have concrete and asphalt at the same time later. So in terms of benchmarking, this is how we actually do the algorithm benchmarking on our data set. First of all, for those deep learning-based algorithms, we training them, and then later on we test them. So how do we train them? We all know the performance of a deep learning model highly depends on the training process and what data set you are using. And to cover a wider range of crack cases, we merge all those public available data sets together and to form the largest pavement crack data set, which has about 11,000 images overall. We also add some non-crack images out of a data balance point of view. So we put them into the 3 deep learning models, including the deep crack, the VGG as backbone, the UNet model with VGG 16 as backbone, UNet model with ResNet 34 as backbone, and then we train them until the model converge, and then we test our collected data on this. In terms of how we test it, it's there's a small tricks over here, because the images we capture is very, very large, and we don't want to downsample them to sacrifice the resolution. So we split them into small patches, and we test each patch individually, and we then merge them together, as what I'm showing here. So this is how we carry out the testing. So about the evaluation matrix, we're using precision recall and F1, as most of other people use over there. And then, so we also allow 2 pixel tolerance on errors, because when we are labeling the data set, sometimes there is just some human error inside. So if the algorithm can successfully detect the pixels within like 2 pixels margin, we will see it's this is true positive detections. And yes, this is how we do those benchmarkings. So in terms of implementation details, when we train this, we have 4 models, the 3 deep learning models we mentioned, and also a localized threat holdings. The localized threat holding model is using the code provided by the author, and it was written in MATLAB. And for the 3 deep learning model, we build them in PyTorch, while the deep crack model is provided by the authors. And for the 11,000 images, we also do quick data augmentations. This is also a conventional technique we use to just avoid overfitting while the training is. We try to kind of do some small twist of those original images. So we rotate the image randomly from 0 to 360 degrees, we flip the image horizontally or vertically, and we randomly change the lightings and just make them look quite different to original ones. We split the training and testing into like a 7/3, and then this is the crack ratios. Like we have about 5% of cracks overall in the pixels. So this is the implementation of trainings. Let's have a look at some results. Overall, I would say the result is definitely not as good as those claimed in original papers, which is typical because we're now testing in a new data set. So this is a comparison of concrete pavement images and asphalt pavement images. We can see that the F1 score, the asphalt, is typically higher than concrete, and then the position asphalt is the position value, which is this column, is typically higher. Oh, you cannot see my mouse. So this column is typically higher than concrete. This is because in concrete pavements, we have something called concrete joints between different patch of the pavement, which is quite similar to crack, and most of the algorithm cannot distinguish them successfully, which I will present in the visual result. But overall, asphalt pavement has a higher F1 score. And if you look into those 4 algorithms, the localized thresholding, which is the one we use traditionally, has very, very low F1 scores and precision recall compared to the other 3, meaning that it's probably not going to be very competitive and applicable to the in practice. And also for the comparison between vertical and forwarding viewpoints, we can see that vertical viewpoints overall has a better score over here compared to the forwarding. So meaning that if it's possible, maybe capture the pavement crack images vertically will help the algorithm, will just make those models life easier. So the overall performance is that asphalt pavements is easy for the model, concrete is quite hard, and this is something not a lot of people pay attention before because they don't really separate concrete and asphalt pavement. Let's have a look at some visual results. This is the asphalt pavement detection result with forwarding viewpoint and downwarding viewpoint. So those images, the black pixels are the true positive, while the right pixels are false positive. And we can see that the localized thresholding is kind of like a failed badly because, like, looking into image 2, it does not detect anything, even though it's quite obvious there's a crack in the images. And then there's quite a false positive in the deep crack models, which happen to have very high precision because they can just capture all the details, but they have quite a lot of false positive detection results. Yeah, and so asphalt pavement is so far so good, but when it comes to concrete pavement, there's quite a lot of problems. So if you look into, you can see quite a lot of red pixels in all different algorithms. Those red pixels, as I said, is a false positive. And they came from mostly those concrete joints. So basically, what this means is that for most of the crack detection algorithm, they cannot really distinguish concrete joints and those cracks. And even though you have trained with a lot of well-labeled data set, you still can do this to acceptable standards. And again, the last column, which is the localized thresholding, it just failed completely. So our conclusion is, first, the deep learning-based method outperformed the traditional image processing method. So the trend of moving to deep learning instead of stick to original traditional image processing might be a legitimate and a reasonable move. And the second one is most of the algorithms perform poorly on the proposed concrete pavement images, which So as I said, this is because it's quite hard to differentiate the cracks and concrete joints. And there's not a lot of researchers focusing on this perspective. And also the vertical viewpoint is better compared by looking to those results if it's possible. So we should capture image at the vertical viewpoint. Some of the future directions we're proposing here. So first of all, we probably can focus on developing algorithms specifically focus on concrete pavement images. And we probably can capture more images of concrete pavements and labeling them well and use that to train the model. And the last one is the domain adaptations. What I mean here is that the entire training scheme we use here is training a data set, training the model with a data set from the public available data set and test it on our own collected. This is actually not the right way to do training and testing. So we are expecting training and testing are all performed on the same data set from the same source. As you can show in here, like the bicycle over here, the top bicycle and the bottom bicycle, they're all bicycle, but they're from different domain because they have different style of images. This can quite badly impact the performance of the algorithm. So, but there are some domain adaptation techniques we can use to kind of like mitigate these problems. So this might be the future directions. So we just train a model with a bunch of available data set and testing on new data set. We can apply a domain adaptation in between to boost the performance. So that's the 3 future directions. The data set is available on GitHub. So you can just search the NHA12D and you can just find it on GitHub. That's it. Thank you so much for your attention.